Hello, everyone, and welcome to today's webinar. My name is Chris Neva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Sasha. Sasha is a Munich-based key account manager at Thermal Analytics, bringing 20 years of expertise in aerodynamic and thermodynamic CFD simulations. Specializing in the automotive and aerospace industries, his work encompasses engine thermal protection, brake cooling, human comfort, and battery cooling. With an MSc in aerospace from TU Delft with a CFD specialization, Sasha provides technical expertise to major OEMs across Europe and Asia. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation. And with that, Sasha, if you're ready, you may begin.
All right. Welcome everyone to our EV fast charging webinar. We'll talk about the thermal challenges and the impact on lifetime of the battery pack and its components. So fast charging. We'll discuss why thermal management is important. We'll talk about the simulation methodology, how it's impacting battery lifetime. What if you're fast charging in cold conditions? And what impact does it have on bus bars and high voltage cables? Here I have a graph to explain the motivation of the study. So we see here the fast charging comparison of different brands. And in green, you have the amount of kilometer that you can charge in 10 minutes, and then in blue, an additional 20 minutes. This was from May 2024. What you can see is that there's quite some variety in the amount of capacity that you can charge. This is, though, a very important parameter of a car. It's important for the OEMs to have good fast charging capabilities. Here, this chart is explaining that for fast charging, you can compare the amount of power applied. This graph is a little bit older, from 2022 and 23. But it's showing that there are quite large differences in the fast charging power that can be applied between cars. So the more power you can apply, it generally means the faster you can charge. But since we're all thermal engineers, we know that more power also means that you're generating more heat, and we need to manage that. All right, so therefore we'll look into the simulation methodology for battery thermal management with Titherm. So the design of a battery pack is to keep the temperatures approximately, or ideally, better said, between 20 and 30 degrees C. But also you want a uniform temperature distribution. And you want to simulate realistic drive cycles. So in this time animation that you see here, it's a realistic drive cycle with several fast charging or occurrences. And you see at first that the temperatures, especially during the fast charging, they go quite high to 50 degrees C. But also you see that there's not a uniform temperature distribution. And this is important, and I'll talk about that later. Okay, so you want to optimize the design, change the materials, add conduction plates, or improve the conduction, or apply liquid cooling. So all these can be analyzed. So we want to do 3D transient simulations. If you do 1D, many people are using 1D systems for the battery model, so that is very nice. You can do long transients, But in the end, it's only 1D, and you don't really get the temperature distribution. For the temperature distribution, often steady-state CFD models are used. However, that is, you don't get the transient drive cycle when you do that. So we're combining those different scenarios where you have your 1D model that is controlling the battery for a drive cycle, where you have your current here over time that goes into the battery pack, but also you want to control the cabin comfort. So how much energy do you need for the cabin? Because this is in the end all impacting your energy consumption. So with that, we can look at battery packaging integrated in the vehicle, do realistic drive cycles, optimize the cooling system, put the cells in series and parallel, look at hot soak, fast charging, thermal runaway, battery lifetime, and energy management. So we can simulate all the different battery cells, so pouch, prismatic, cylindrical, and we can look at cell level, module level, pack level, or even vehicle level. That is all possible. For the battery modeling, we have our own battery model where that we are coupling to the thermal solution. So this is important because resistance of the cell is a function of temperature and depth of discharge. And the resistance, as we know, influences the heat that's generated through I square R. So it's important to do this two-way coupling. And the battery models that we have, so we have the equivalent circuit models, NTG, or the NREL equivalent circuit model that has two additional polarization resistance terms. All right, I wanted to start with one slide showing a validation on a real vehicle that this study was done by Cirrus and published at SAE. There's a lot of nice slides in there because they did a validation of a full battery pack. And here are the results for fast charging. So we're applying a typical fast charging profile over 35, 36 minutes. And these are the thermocouples in different locations compared to experiment. So the temperatures go up. And you see the peak is very nicely predicted. So this is a typical peak during fast charging. And then because the current is lowered, then the temperatures drop again. Peak is well predicted. A slight offset for this one thermocouple can be due to soak or natural convection effects. But yeah, especially here, the peak is predicted well. All right, so having showed that validation, I want to show a bit more fast charging case studies where we're doing a realistic drive cycle and see how this is impacting lifetime. So we have implemented NREL's blast light lifetime model. So that is from the National Renewable Energy Laboratory. They have developed this lifetime model extensively. They do a lot of testing and validation. And this is their latest model that we have included. And the nice thing is it has a library of battery cells for lifetime and degradation performance, because this is often hard to obtain. So we have that available. This newest release includes C-rate dependence, which is important for fast charging. And then, as the typical lifetime model, we're including calendar and cycling fade. So these are different degradation, as the calendar fade is mainly when the cell is stored, so not used. It's losing capacity. This is a function of temperature and state of charge. And then we also have the cycling fade, which is when you actually use it, so charge and discharge, which is a function of the delta state of charge. So how much do you charge and discharge? At what temperature? What delta temperature? So yeah, this is what we're using. And the drive cycle, we're trying to do a realistic 1 week drive cycle, where during the week we're driving to work and back, and then during the weekend a longer trip, and we repeat this every week. And then we're comparing what if we would do fast charging only, because not everyone has a charger at home. What if we would do slow charging only, and what's the impact of the cooling system, and how this influences lifetime and range. All right. So here is an overview of the current over time. On the horizontal axis, we have days. So 7 days, that's 1 week. And this is the current. So just going through the plot. On day 1 in the morning, we're driving to work and then driving home. On day 2, but then we need to charge already. So then we're comparing a slow charging against the fast charging. Day 3, day 4, and then as mentioned, during the weekend we do a longer trip, which requires driving, more intense driving, highway driving, let's say, with 3 charging occurrences. And in green we see the fast charging, 3 fast charging, comparing to the slow charging, 2-hour slow charging. And on the Sunday back, and here this is the state of charge on the right axis. So yeah, when you're fast charging, then you're charging quickly. So between 0 is empty and 1 is full. So 1 for slow charging. We have those differences. Okay. Here are the temperatures. Again, for the 7 days. So during the week here, we see clearly the fast charging temperature peak, where the temperature goes to about 50. But then you see during the longer trip, where the driving, we have a highway driving. So then, especially during, the temperatures are already higher, but during the fast charging, the temperatures go almost to 60 degrees C. When you do slow charging, the temperatures still increase. It's a 2-hour charging, but not as much. And then here in the dotted lines, just as a comparison, so what if you have improved cooling system? So let's say a very good cooling system, then the temperatures remain around 25, 30 degrees C, whether you're fast charging or not. So I thought that was very interesting. And this is the impact on lifetime. So here is the time in years, this time. So we're predicting the capacity loss over the years, taking into account different seasons like summer, spring, winter, and the capacity. So 1 means a full battery, and then 0.9 is 90% of capacity, so 80%. So you have less and less over the years. And if you would do this cycle every week with fast charging, you see that the capacity drops really quickly. You reach 80% after 5 years. That has a big impact and a big difference also comparing when you do slow charging. And so then it's like 80, even above 85 after 9 years. So that shows the impact of fast charging. And then say you would have, let's say, a very good cooling system. Then you see actually almost no difference between fast charging and slow charge. That is shows how important the thermal management is. All right. Here showing state of charge for the week. So how full is the battery for your cycle after 1 year, so when it's new, and after 5 years for this fast charging profile that degraded so fastly after 5 years. So you're doing the same cycle, starting with almost 90% full battery. But you see, after 5 years, your battery is depleted more, 10% more, and this could get worse. You might not even be able anymore to drive to work. Then finally, I wanted to show the 3D transient analysis, the temperatures. And we have a cooling plate underneath, which you also see. So cold liquid in on one side, going to the end and then back. So this leads to large temperature differences within the pack. We see the maximum during a peak. In the weekend drive, it's 48, and the minimum is 34. And typically OEMs aim for like a maximum 5-degree delta in a pack. But this is for large packs. This is very difficult, and we have already seen the impact on lifetime on such a big temperature difference. So that means that the cells that get warmer, they degrade faster over the years. So after 5 years, these cells would be more empty than the cool ones. Right? So this requires thermal management optimization. All right, so we've shown the effects of the cooling system, fast charging, lifetime. You can improved cooling leads to extended lifetime range, but also you need to look at the non-uniformity of the battery pack. So this is also very important. All right, the next topic is fast charging in cold conditions. So now the ambient temperature is minus 18 degrees C, and we want to see what is the impact of insulation on the outside, because it's cold outside. So what if we put insulation, and then you see here a drive cycle. It's a different drive cycle. Let's say you will be driving here, and then you let it parked outside in the cold, so soaked. And you see that with insulations, the temperatures drop much more. We almost reach minus 18 in the morning, and then we want to fast charge. Now, if the battery is very cold, it will be a problem to immediately apply fast charging in the morning because you cannot apply that much current in cold conditions. So that's the study that we're looking at. So this is the morning where you want to fast charge, but without the insulation, you are starting at minus 18, while with the insulation, you're 10 degrees higher. So if you want to fast charge, you need to heat up your battery. It's very important. You need to apply, you can only apply current when you have higher temperatures. So you need to heat up the system first. And if you have a slow heating system, then you see the temperatures of the cells also will slowly heat up. While if you have a good heating system, the temperatures will increase faster, which makes a big difference, especially when you're starting at -18. At -10, you also see this effect, the cooling system. Now, this is important because it influences the amount of current that you can impose your fast charger. I showed it in the beginning. So the more power you can apply, the faster it goes. But if your cells are not at the right temperature level, then you can only slowly increase the current. You see here, if you're able to increase temperatures, you go faster. But if you have insulation, like the yellow curves, you can apply even more current. And this influences your charging time. So state of charge, how full is the battery? It's 10%, so almost empty. How quickly do I reach 80%? And you see, if you don't have a good heating system and no insulation, compared to a good heating system and insulation, so you can gain like 10 minutes of fast charging time, and 10 minutes on 45 minutes, it means a lot. It's very, it's a big impact. All right. Now just showing the results. What if we precondition the battery, which is this green curve? So you can say, okay, I'm going to drive in the morning, precondition my battery to 25 degrees C, and then you're going for the fast charging. So you see the temperatures are much higher, more quickly. You can immediately impose a high current, which is good. And you see this improves the fast charging time even more. So you see the difference between those different scenarios. All right, so showed the effect of insulation and the effect of a good heating system on fast charging, performance in cold conditions. Insulation helps, but especially the heating system is important. And of course, ideally, you want to precondition before fast charging. All right, so now next we want to look at some components and how they are impacted by the fast charging. So for example, the bus bars. So we're applying here fast charging profile again, high current, over 40 minutes. And then we just want to do a sensitivity study of bus bar thickness, material width, thermal link contact resistance, cooling plate, insulation, cooling, etc. So we have a similar battery pack in series and parallel. We apply the Joule heating here. So we have a Joule heating capability because we're applying current through a material, and then the material has a certain electrical resistance that depends on the type of material that you apply, like nickel, copper, aluminum. It also depends on the shape and the area. And then you obtain the heat from the Joule heating through I squared R. But the resistivity, the electrical resistance, is a function of temperature. So therefore, it's again important to do this two-way coupling. And applying this, well, start with varying the thickness for a copper bus bar, 1 to 3 millimeter. So here are the bus bar temperatures over time on the left. We see that 1 millimeter goes to quite high temperatures. Well, it makes sense because it's very thin, so low mass. But with 2-3 millimeters, the temperatures are lower. The bus bar temperatures only minimally impacted the average cell temperature. So it's really mainly about the bus bars. What when we're comparing copper against aluminum, which have a different electrical resistance? So here we see the aluminum goes up higher. Yeah, again, aluminum is lighter, so it's not just the difference in electrical resistance. But that was for 1 millimeter. So what if we vary the aluminum 1 to 3 millimeters? So here again, we see 1 millimeter, the highest temperatures. The bus bar width. So yeah, you can have very wide bus bars or thin. So we compared 50 millimeter with 25 millimeter width. And you see that the thinner ones reach higher temperatures. So again, weight and heat play a role there. Thermal link sensitivity, so this can be interesting for the users. In TiTerm, you have the possibility to apply a thermal link between the bus bars and the cells, and that means you're allowing conduction between them without creating a mesh connection. So just say within a certain distance they should have conduction. And then the question is, what is the contact resistance? So how well are these materials conducting? How well are they connected, like they're welded? So we're comparing some values here. And we see that with a very high contact resistance, which means there's not much conduction, which is not very likely, I would say, you get higher temperatures, while the difference between the two lower contact resistances is minimal. So I think that's a good sign because they are well connected. So you don't have much uncertainty there. Okay, what if we put insulation between the cooling plate and the cells? So here, if you have no cooling, temperatures stay high. If you have cooling plate but insulation between, then temperatures are lower. But of course, if you have direct cooling, direct contact between the cooling plate, then temperatures are lower. And now it's also impacting the batteries, which makes sense. What if you have insulation around the battery casings? Because for thermal runaway, you might put mica sheets around, so we have varied that. And by the way, you can very easily add those different layers without really meshing. You can add them virtually and define the thicknesses, which we can do for the bus bars and the cells and everything. Yeah, now we see that when you put insulation, the temperature, you're protecting the cells for thermal runaway, but you're storing more heat in them, so they are really higher, except much higher than without insulation. And the same for the cells, so I think that makes sense. All right, so here just a summary of the busbar designs that you have here. So you see that the busbar thickness had a big impact on the maximum temperature. But of course, also like cooling or insulation had big impacts as well. So yeah, these are easy to evaluate because the 40-minute of fast charging scenario can be run in 10 minutes on a local laptop. Okay, the final part is looking at the high voltage cable. So you all recognize this fast charging cable that is connected here in the socket, and then you have some electrical cables that lead to the battery pack. So it's important, there goes high current through, and it all gets very hot. Again, we're applying joule heating capability. Here you see a close-up of the geometry where we have the socket, the connector, applying the fast charging profile all transiently. And we have also a cooling system inside because the temperatures get so high. So then here on the left, you have the scenario without cooling, and on the right with cooling. So you clearly see the temperatures get much higher without the cooling, while they are in reasonable range with the cooling. just zooming in. So here, especially here in the connection, there it gets quite hot. And this is the imposed heat from the Joule heating that we impose. So we have a contact resistance. We're including that heat, and yeah, that is included. And then you have the voltage drop over the cable that you can predict. All right. Very good. So that brings me to the end of this webinar where we showed the battery thermal simulation capability overview with time term and how we can do 3D transient realistic drive cycles. And then look at battery temperature range, uniformity. How can we improve this? We've shown a validation. How is this impacting lifetime? And optimize the design yeah, for either cold conditions, temperature levels inside the pack or the bus bar and the high voltage cables. All right. Thank you.
Thank you, Sasha. We can go ahead and open it up to some questions now. See, first one here. What is the benefit of doing 3D transient simulation of battery packs compared to 1D or 3D steady state CFD?
Yeah, yeah, good question. So, yeah, I think this slide shows that. I think what we have seen, especially for large packs, is that the temperatures vary a lot during a drive cycle, and yeah, most people are doing 1D, but you don't model the pack with all the different cells and the conduction through the pack. Maybe even radiation, the convection, the local convection effects are very difficult to model in 1D. And I think here, especially this graph, you see a large temperature gradients. And the peak, the maximum temperatures, they only appear during operation, during fast charging. So they're not steady state either. All right.
All right, thank you. So next one, for cooling simulation, is it a coupled simulation or a standalone simulation in Tyther?
Oh, the examples that I showed are using the fluid streams. So there was one slide where you define an inlet and an outlet, and then all the temperatures of the coolant are calculated over time, and you can make the inlet mass flow a function of time and everything. So this is a nice approach, especially for channeled flow. But you can indeed also couple with CFD, where you can make the convection a function of time, right? I wouldn't recommend to do 3D transient CFD for the cooling, but you can import at certain time instances the convection and do that. So it depends what you would like to do. Yeah, both for the liquid as well as the surrounding, you have the options to couple with CFD, but I would do it at certain time instances and not fully transient, because then you lose the benefit of doing a fast transients in Tyther.
All right, thank you. How can I obtain the battery lifetime characterization data?
Yes, good point. We have a library of several cells with battery lifetime data, and they're really different types of cells. So I think that covering quite well already what is currently mostly used on the market. But of course, getting the characterization data, that would require some testing of the cell, can be obtained from the battery cell manufacturer. There are some companies that offer lifetime data, there are online databases, but I think the nice thing now is that we have this lifetime database of several cells.
Thank you. Do you have your own battery management control systems?
We have our own battery equivalent circuit models, so where you can put the cells in series and parallel and apply current profiles. So that is what was used here. We have some control strategies for that, but alternatively, you can also couple to your own battery models that you might have. So your 1D system tools in MATLAB, GT, MSM, all the 1D tools, we can couple through FMI, FMU, and then we can do this two-way coupling. So the 1D system would provide not just current, but for example, also cooling rate, cooling system rate, inlet temperature of the coolant, mass flow. And that then is feeding back the temperature of the cells. So say the maximum temperature of the cells is fed back into your 1D system. Because if the cells are too hot, you need more cooling, or if it's fine, then you don't want to apply that much cooling to save energy. So that's another way of controlling your battery pack.
All right, thank you. We had a very long one come through, so I think maybe we'll follow up with that person afterwards. It looks like we'll do it for questions. So thank you everyone for attending. We appreciate that. You will receive a follow-up email this afternoon containing a link to watch the recorded webinar session. Again, thank you everyone, and have a nice day.